Welcome back. So let's continue with this slide. There's no better way to summarize what we've been doing. Select from where group by having order by limit offsets by heart. Does anybody know what this query actually does? Imagine I'm in the Federal Office of Statistics, and I have the database with 8.5 records, one for each inhabitant of Switzerland. And I'm sitting in front of my computer, and I input that query in the database. What does it do? So I have all the population of Switzerland, one record per person. I have the city where they have a house in, and then whether tenant or owner, and then marked by residence, first, second, and so on. Group by city, having the counts more than 100,000, order by population desk, limit 10, offset 20. Anybody? On Zoom, maybe? Nobody? All right, let me tell you. So it's going to output the cities of Switzerland sorted by population, but only rank 11 to 20, because I'm skipping the first 10. So Zurich, Geneva, Bern, Winterthur, Basel, they're all not included. I'm going to have the 11th, 12th, all the way to 20 with the name of the city and the population, right? Because what I did is I aggregated the population by city where they have their first residence. And sorry, what I forgot to say is I'm only considering those that have more than 100,000 inhabitants. And now I'm starting to think that I might get an empty result because I think that there's less than 10 cities with more than 100,000 inhabitants. Oh, yes, that's a good point. Why not 2030? Yes, you're right. Offset 20, so it's from the 21st to the 30th. So in Switzerland, you will get empty results because you will not have 21 cities with more than 100,000 inhabitants. Let's say it's worldwide. I do it worldwide with the entire world population, fits on a machine, by the way. And I would have the cities from the 21st to the 30th ranked by population, right? All right, I think I got it right this time, right? Okay. Who understands this query? Okay, awesome. Good. So again, the point of that is to show you the clauses, select from where group by having order by limit offset. And you're already 80% of the way knowing this, yes?
Question is that this will be empty, will I get an error?
I think it would just be empty. If you don't have anything to return, it's just an empty table. Yeah. But I don't think it would output an error if you go beyond the records. Oh, by the way, it brings me back to the question you asked earlier, because Bowen checked on the average. What happens with average if you have nulls? And the answer is that you ignore the nulls. So for example, as Bowen was saying, if you have 5 records in a group, 1 is null and there's 4 that are not nulls, it's going to be the average of the 4 that are not nulls, and the null is just ignored. If you want, Bowen, you could double check if you try to issue a query with a limit and offset beyond the size that it doesn't return an error but an empty table. Maybe you could validate this. It would give an empty table. Yeah. All right. So you agree with me. Very good. Okay, you're welcome. Any other questions? Okay. Good. So that's a very, very good milestone. So now you can really play with this all you want in the Jupyter notebook and try to make it work. So now I'm going to more advanced features of the SQL language, sort of things we can do. You might remember the joins where I have 2 tables and I want to match the records of the 2 tables together. The typical use case is that I have a primary key and a foreign key, like a list of tax declarations with the social security number, another table with persons, and I'm matching the tax returns with the persons. It's this symbol with the join that looks like infinity, but with straight lines, right? Okay, so that's the theory of joins, and I'm basically matching, you see, just so that you remember, here it's a natural join, so I look for the columns that have the same name, B and B, and here I match one through the one here with the one there, so I join that record matched with that record. and this record match with this record, and so I get this joint table. That we've seen, right? We've seen it before. We have, so this is a natural join, and we have the theta join, where I explicitly specify my predicate for matching two records. Here I match A with D, basically. Okay, how do we do this with SQL? Well, first I have good news. We can already do it without introducing anything new, just with select from where. So how can it be? Well, the trick is that in my from clause, I put the two tables. Select from person spaceships, all of them, and then I specify my predicate of my theta join in the where clause. So this is what I'm getting. But let's try to understand what this is doing. First, the from clause. What does it do? If I do select from person spaceships, technically it's going to compute the Cartesian product of persons and spaceships. So I have 4 persons and 4 spaceships. How many in the Cartesian product? 16, exactly, 4 by 4. So technically, after the from clause, after I evaluate that, I have 16 records. In these 16 records, I filter for them such that the person's last name is the same as the spaceship captain name. This is where the join happens. Again, it's a theta join because I specify the predicate explicitly. So it means that I'm associating Kirk here, this one Kirk with this Kirk with this Kirk, that's the second match, Picard with Picard, that's the third match, and Janeway with Janeway, that's the fourth match. So I have 4 matches. Out of the 16 in the Cartesian product, 4 survive. And then once I'm done with eliminating this, I need to do the projection in the select clause. I project to sentry and warp. So sentry comes from the left and warp comes from the right. So you see 23.5, 23.4, these are the Kirk vessels. There was Enterprise A and the original Enterprise, so 5 and 4. 24.9.2 is the Picard match, right? And 24.9.975, yes, warp 10 is the maximum, and they get closer and closer to warp 10 as the seasons go. So that's Janeway, the last one, right? 24 and 9.975. So this is how we get this table. Who understands that query? Okay. It's incredible because we managed to do a join without introducing any new syntax, right? So this is the easiest way to actually join two tables. And now you could imagine, in that case, I didn't speak about primary keys and foreign keys, but in general, you could imagine that the persons have some key like the social security number, and then I identify the captain of a spaceship with a foreign key with the social security number of the captain, for example. Here I use the last names because there are few people, so we can just identify them with last names. All right. So that's it for this query. Now, let me tell you something. There is actually a syntax for joins if you want to explicitly use it, and that's pretty much the same thing. So the difference is that instead of using the where clause in this way, to specify, to basically do a selection on a Cartesian product, in the from clause, I use the join keyword. Persons join spaceships on last name equals captain name. It's the same thing. It's just that in that case, I explicitly say that's a join. In that case, I implement the join as a selection after a Cartesian product, right? Who sees that it's the same thing, right? It's just two syntaxes, and you can pick whatever you prefer, right? Some people like this one because it's a good old select from where, and some people prefer that one because it makes it explicit that there is a join, right? It's really a matter of taste. Now, you might think, this is more efficient than this, right? Because here you join and here you have a Cartesian product. That's not true. And the reason it's not true is that when I explained to you the Cartesian product with the 16 values and so on, that was just a logical reasoning in my head. The computer is not actually going to do this. The engine, PostgreSQL, is smarter than that. PostgreSQL will see, okay, we have a Cartesian product followed by a selection. It will automatically detect that it's a join, and it will actually implement it as a join. So it's going to be just as fast as this one, right? That's the power of a declarative language where the engine actually detects things and figures out things in order to do it efficiently. So this is really the same speed, the same results in the end. That's called the table expression, right? Because it's in the from clause. I basically have a table persons, a table spaceships, and I join them in this way, right? So the difference between the other clauses is that the other ones, so select from where, group by having, order by, limit of set, they are like vertical, like all together, but join is nested within the from clause. That is one of the differences, okay? Now, what if I want the Cartesian product explicitly when I can do it with a comma, right? Persons, comma, spaceships. But you can also use the keyword cross join, which does the full Cartesian product. I didn't take 4 by 4 because 16 was a bit much, but I took 2 times 3 in that case. So this is the Cartesian product of the two tables. 2 times 3, I get 6 of them. Cross join is just the keyword for Cartesian product. Cross, you know, that's the notation for the Cartesian product. Who understands this? Right? It's a good old Cartesian product. No selection. It's really just all the combinations left and right. This is the same. It doesn't matter, you have a comma, you have a cross join, it's just the same thing, right? It's really, some people like to be explicit, some people prefer to just abbreviate a little bit. It's really a matter of taste, and I don't have any particular preference. It's up to you. Now, there's a few variations that I'm going to show you. We have what's called an inner join. An inner join means I'm going to match the last names with the captain names and get that, right? This is what I get in the end. Why inner join? It has to do with the nulls. It has to do with the nulls. In that case, I don't have any nulls, so I don't really care, right? But in general, imagine what did I do here? I basically let me correct myself. It doesn't have to do with the nulls. It has to do with the records that do not match. Look. Kirk, there's a match. Picard, there's a match. Janeway, there's a match. But I took that perspective. Now, let's take the other perspective. Here, Kirk, there's 2 matches. Picard, there's a match. Janeway, there's a match. Crusher, there is no match. This one is left alone. So if I have an inner join, which is the default, so a join, you see that Crusher, Beverly Crusher, is nowhere to be seen here. So the tuples that don't match, they're just excluded, right? So this is what an inner join does. The outer join is going to also include the tuples that do not match, and they are just going to put nulls everywhere. So it does have to do with nulls, but in this way, that I'm basically populating everything with nulls. So now you see that because I said outer join, it's going to include this in the output here, but since there is no match in here, it's just filling with nulls. Does that make sense? And now, why did I say left? Because I want to do it from the left side. So the tuples on the left that don't have any match, I fill with nulls. I could also have said full outer join to do it on both sides, right outer join to only do it on that side. Yes?
Why don't we have the other proposal of the
Oh, that's because of the filtering criteria here. I say on person's name equals spaceship's captain name. So this is why it's actually filtering and only matching, right? That's the difference with the cross join here, where I don't have a predicate and it's all combinations, right? But this is really because of this here that we only take the matches, right? I'm saying the person's last name must match the spaceship's captain name. So I match Kirk, Picard, Janeway, right? And if I have an outer join, this one doesn't have any match. I still include it in here, but with nulls all the way, right? But the only reason it's here is because it doesn't have any match, right? I wouldn't match it with the 4, that it has nothing to do with this 4, right? So I wouldn't output this, that I don't output. I really just fill with nulls. Did I answer your question? Does that clarify? Yeah. Other question? Yes?
right outer join. Then
Yeah.
you take everything from the rows in the spaceship and then match it to the first.
Yep.
But we don't have crusher in the right table. Also happen to crush the row with crusher.
Then if I say right outer join, then this disappears. Yeah, actually, right outer join would be the same as inner join. It's just because here they all match. All of these 4 have a match there, right? I might have, I think I made an example. Here, I removed Picard here. which means that now we have a spaceship that doesn't have a match there. And now I put right outer join. What's going to happen is that now I fill Picard here that doesn't have any match with the nulls over there, right? That's what happens. So the outer join is a way to preserve the records that were not matched anywhere. That's what it does. And I can say only the left, only the right, or full outer join, then I do left and right. Here I have Crusher without any spaceship. I have the Enterprise D without any captain on the left. And you see that I have sometimes the nulls on the left, sometimes the nulls on the right. That's a full outer join. Okay, you understand? All right. So inner join, I drop the records that don't match. Outer join, I preserve them, but I put nulls on the other side because they don't have a match. Okay. Now we have the natural join. And again, you remember it's when we have the same column name. So here I have last name in common. I changed a little bit my data. So last name, last name. Now I can just say natural join or even natural full outer join if I want to be extremely explicit. And that's just going to do this, right? Here, the predicate is implicit because I really just match the columns that have the same name, right? So this is why I don't have this on part. For whom does that make sense? Yes? Okay, so that's a natural full outer join. Then you have the natural left outer join, the natural right outer join, the natural inner join, and so on and so on, right? So you can just do all the combinations. Here's the natural inner join that would just not output it. Oh yeah, I have an example here. What did I do? I put columns that don't have different types, just to warn you about that. Here I abbreviated century as C, and the code for the spaceship as C. Now you see what happens. I'm trying to do a natural join, but I have C and C that would also try to be matched because I wasn't careful and I didn't look. And so now this is empty. The natural inner join is completely empty. There is no match at all. And because it's an inner join, I don't put them with nulls, okay? So be careful. If you do a natural join, you really need to make sure and double check, look at the tables and check that the column names in common are really the ones you want to join. If you're not careful, that could happen, right? All right, now I'm back to century and code. Now I have a full outer join with a natural join, right, using last name. So just so that I explain. Full outer join, you know, full outer join means I include those that do not match. So here I have Crusher filled with nulls, and here the Enterprise D filled with nulls. But what is new here is the using. Here, I'm basically saying, instead of my own criterion, I want to say explicitly the columns that I want to match that have the same name. So here I'm saying the last name columns I want to match, and then it's going to join on there. I could have done this here to fix it. If here I would have said natural inner join spaceships using last name, then I would have specifically said these are the columns that I want to join that have the same name. So that's how you can fix it. Okay. Okay. And not sure what I did here. Using last name. Yeah, I think I should drop that slide. I don't even know what I was thinking. Maybe a copy paste anyway. If you have columns with the same name, what you can do is rename them. So if you put an as here and you want to avoid the collision, you can say as p name, as s name. So now you're changing the name and then using last name, and then this is what you basically get in the output, right? Now I remember what I meant. So now I can rewind. Just need some time to recall what I wanted to say. So now I can tell you what I wanted to say. I'm computing the natural join of these two tables using last name as the values that I want to match. So it means that I am matching last name in here with last name in there. The problem I have is that if I do that, I'm going to end up with a table that has the name coming from here and the name coming from there. But you might remember that this is forbidden in the relational model. I cannot have twice the same attribute name. You remember that, right? So here I have a problem. If I actually try to do this, I'm going to end up with a table like this. And I want to avoid this, so I should explicitly rename them to two different names in order to avoid the collision. And now I'm good because I have different attributes. Does it make sense? Okay. Now, a word of warning, if you don't do it, I'm pretty sure PostgreSQL will not complain. And I think if I correctly remember, it's going to call one name one and the other one name two, right? So it's just going to make up things to give them names. It's not a good idea to let PostgreSQL do that. You should really be careful, anticipate on that, and really give them the names you want so that it doesn't create attribute names for you. Okay? All right. So do you see how I disambiguated, by the way, in order to say that I want to rename the person's names as P name and the spaceship name as S name, I use this little dot in there with the name of the table, persons.name to disambiguate that this is the one, spaceships.name to say that this is the one, right? I can also use a shortcut like persons P, just adding in here and spaceships S, which allows me to just use P and S, right? And then this is what I get. Okay, so far so good, everybody following? This is getting more advanced, right? Now I keep making it more complex and more complex, right? But you will play with Jupyter notebooks, you will see it. It's going to feel great when you actually use it. Now, we have something really nice that's called a self-join. You can join a table with itself. An example of that is genealogy, right? You could have a list of persons with the parents, the children, and so on, and now you can join the table to get back all the ancestry relationships. Now, I'm going to do a self-join because the spaceships, they have successors, right? So the enterprise A, the successor of it is enterprise B, the successor is enterprise C, the successor is enterprise D, enterprise that was the first one, the successor is the A, and enterprise D has the E as a successor. So this is the successor column that refers to the same. So basically the code is the primary key of the table, and successor is the foreign key that points back to the same table. Does that make sense? So for the successor, I use the code of the successor. And what I can do is then write a query like this that has spaceships, inner join spaceships, but now I call one S1 and the other one S2 to just disambiguate them. And I'm saying that S2, the code, must match S1 point successor, right? So this is how I match the table to itself. And then I'm going to get all the combinations, but now with the names, right? I output the name of the former and the name of the next one. And now I see enterprise, the successor is enterprise A, the successor is enterprise B, and so on and so on. And I don't have enterprise D as the former because it's an inner join. If I had an outer join, there would be enterprise D with a null, right? For whom does that make sense? Right? It's just a self-join, and I can do it recursively even more times and so on, right? That's one of the perks that you can join the table with itself. The way you do this is you just use the same table name on both sides of the join, right? Here, spaceships on the left, spaceships on the right. You can absolutely do this. Now, there's a lot of combinations. If you don't say anything, like with a comma, it's going to assume cross-join, the Cartesian product. If you just say join without anything else, it's going to assume an inner join. So it's not going to put those that don't match. If you just say left join, it's assuming it's a left outer join. So it's just an abbreviation. Right join is the right outer join, and full join is a full outer join, right? So some people just say left join instead of left outer join to shorten a bit the query. Okay, that's the joins. That's quite a lot to digest, right? Who understood the joins? Okay, very good. Play with the queries, really use tables. In fact, the exam data sets that we used in previous exams, they are made in such a way that the table point to each other. For example, you're going to have artists for that play music, so artists, then another table with the releases, with each album, for example, then another with the tracks of the albums, and you can join the artists with their releases and the releases with the tracks. The way you do that is that you have artist IDs. In the releases, you have an artist ID that is a foreign key pointing to the artist. In the tracks, you have a release ID that points from the track to the release, and you can join 3 or 4 tables together, right? So this is something we commonly do at the exam. So I recommend you look at these data sets. You can look at the past exam queries and train on that. right? Again, it's very, very common to join tables with each other, and very often you're just doing it with foreign keys and primary keys. That's the typical way. Okay, now set operations. That's going to be easy, much easier. So you remember that I can compute the union of two tables in the set, bag, or list semantics, doesn't matter. I can just compute the union. How do I do that with SQL with the union keyword? The way it works is I have a select from where that gets me a first table, a select from where that gets me a second table, and I just union them like this. So again, the syntax is select from where, group by having, order by limit of set, blah, 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 union, and then select from where, group by having, the order by limit of set, and so on the right. And I just put the union in the middle, and it's just going to compute the union of the two. It does duplicate elimination. Be careful. That's why I only have 5 here instead of 6, because there is a duplicate that enterprise C that is a duplicate, right? So it only appears once. If you don't like the duplicate elimination and you want to back semantics, just say union all. Let me show you. It's just a few slides after that. Union all. This will not eliminate duplicates, right? In that case, you really keep it twice. Union eliminates duplicates. Union all doesn't eliminate duplicates. Okay? And then we have, just getting back, we have also the intersection, which is just select from where grouping, group by having, blah, 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 intersect, select from where group by having, order by limit of set, right? And that's what I get, enterprise C. And then except is the subtraction. There should be an S in there. Subtraction is just those that are in the first one and not in the second one. Do we have a question on Zoom, or you answered? You answered, okay. Okay, of course, word of warning, you should be doing that if the tables have the same colors, right? Here, I'm assuming they have the same color. And unfortunately, and this is something that I have to say makes me very, very, very sad and disappointed about PostgreSQL, but that's the way it is. In PostgreSQL, you even have to pay attention that you declare your columns in the same order. The reason it makes me sad is that in the relational model, the order doesn't matter. So normally they should just be matched. But sadly, if in PostgreSQL you have the columns in a different order, the union, intersection, and subtraction is done based on the order and not based on the column names, right? I'm very sad about it. This is real life, I guess. I don't know why this is it, but that's how it's done. In the relational model, it's really the column names that matter and not the order. In real life, in PostgreSQL, it actually does look at the order of the columns. So that's just a small word of warning that you have to be prepared that sometimes in the real world, you might have a small data independence leak, and that actually happens. Okay? Union all, again, that's for the duplicate elimination to deactivate it. All right, that's the set queries. Union, intersection, and subtraction. And again, you just need 2 select from where statements, and you put union, intersect, or except in the middle. Next, how do I nest queries? And now we are about to unleash the superpowers of SQL that really, really takes it to the next level. Because until now, I only showed you a single select from where, maybe 2 of them with union, intersect. But now we are taking it to the next level by nesting them and building more complex queries. In order to structure your thoughts a little bit, I have prepared it to tell you the story in a specific way. I need you to understand that on the one side, we have tables, relational tables, right, that contain sets of records. And on the other side, I have scalars. What is a scalar? It's just a single value, a string, an integer, a date, and so on. It's a bit similar if you think of linear algebra. You have the notion of vectors, and you have the notion of scalars, right? So the scalars would be the real or complex numbers, and the vectors would be those that are made of multiple numbers. So think a bit like of scalars, just like in linear algebra as the real and complex numbers. So we need to distinguish between the two. If you do that, you will understand that in SQL, or SQL, we have expressions that manipulate tables, and the select from where actually does that. And we have expressions that manipulate values. Where did we see that? Inside the where clause, for example, in the predicate. This is something that works with single values, right? That's an example. So this is why we need to be careful distinguishing between the two. if you do it, you can just come up with all combinations. You can have a value expression that works on scalars nested in a value expression. You can have a value expression nested in a table expression. You can have a table expression nested in a value expression, and a table expression nested in a table expression. And now we play Inception, right? A dream in a dream in a dream in a dream. We start nested queries inside queries inside queries inside queries. Okay? Are you ready? Let's go into it. So I'm going one by one, right? I start with value expression in value expression, and just then I go into the other one. So value expression into value expression, that's easy because that you've been doing since primary school. It's like when you write additions and multiplication, you can nest an addition inside a multiplication and so on. So this you've done already for more than 10 years. It's just that what you have in the where clause or what you have sometimes in the extended projections is just some formula like this that manipulates single values, right? So that's an example of a value. Here it concatenates two strings. Here it casts it as an integer, so you get 34 out of this, and then you add 2, you get 36, right? It's just a mathematical expression that works with single values. There are no tables in there, right? It's a single value. All right? For whom is that clear? Since primary school, you've been doing that, right? This is really arithmetics and so on. Okay. That goes into the where clause. This is one way of putting it when you have your predicate. You can also see that in the on clause in a join that also involves a predicate. You might also see them in the select clause when you create new columns based on a formula. Like this. Here we have a name and we add a dot at the end. And the second column would add 20 to the age column. All right. So this is how we put value expressions inside table expressions, right? In the where clause, in the on clause, in the select clause, and so on. For whom is that clear? Right. That's in fact not new because we've been doing that already last week when I showed you the where clause. Right? This is whenever we have a predicate for a selection, it involves working on values. Okay, but now this is where it gets interesting. Because there's another way you can nest single values, like atomic values, to create a table. What if we could take a few values like this, foo bar 1 and 2, and out of it, create, just on the fly, a table that contains foo bar 1 and 2 in this way. You see, I want a 2 by 2 table, 2 brackets, 2 columns. Let's call them S and N. How do I build that? Well, the good news is that you can do it in SQL. The second good news is you've already seen that a couple of weeks ago. You've already seen that when we did the insert into. Do you remember? Insert into blah, 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 values. That's it. And it turns out that you can use values standalone. You don't need an insert into. You can just go ahead, you can try it in Jupyter, values foo1 bar 2. This is creating a table on the fly like this. Now, because you don't specify the column names, PostgreSQL does it for you, and it's very original. It's calling them column 1 and column 2. Right? You can try it. You will see this is what happens. Column 1, column 2. Text and BigIt, it just figures it out from the values, right? It notices that the first in every record is a string, the second one is an integer, and it does that. All right? This you can do. Again, do it in Jupyter Notebook, it will work. Yes?
What happens when it's like can and then 1 second? Or
it's either an error or it's going to force a cast. Could we try it, Bowen? Any chance you could try to input that, but with mismatching types? Then we'll get back to you. Yeah, it could be either an error or it will just make it fit together. Right? Here's another example where I just put, I reconstitute a table that I've seen earlier in the slides with James and the date, Beverly and the date, and that's what it does, always with column 1, column 2. In that case, it's a text because it doesn't know these are dates, right? In that case, so that's why you get text and text. What's very important is to understand that values and select from where, blah, 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 are interchangeable. Whenever you can put a select from where, you can put instead a values, and whenever you have a values, you can put instead a select from where. They are at the same level. You have a question?
Yes. About the values, when I just click values and put the names in it, how do I view the table of SQL? Just view the table of SQL to look at to select or from and then the name of the table. But now I don't have a name.
Do I have a slide on this? I can't remember. So you mean about how do you create the column names?
No, how do I view it like an SQL notebook? View the table you just created. You have to do like select.
This is going to do it. You don't need a select star. Just put values, blah, blah, blah. And in Jupyter, this comes out without a select star. You don't even need it. Yeah. That's exactly why I'm telling you these two are at the same level, interchangeably. Either you just create the table specifying the values, or you use select. You can, of course, I will show you, you can nest values inside a select star. You can also do the opposite, in fact, as I will show you. But technically, you don't need to. You don't need a select star. You can really just directly go ahead and write values, blah, 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 blah. It just works. And then it's outputting exactly this on the Jupyter notebook, right? It's magic. It's beautiful. Just works. Yeah. Right? Any other questions? Okay. I really encourage you to do it, right? Take the Docker, write these queries, try this, copy paste this, and it should just work and give you exactly this, right? Okay.
Yeah, but after for these types, I mean, I think the SQL parser will reject it when they expect the types of the scalars. I will say, okay, in the first step, we'll say this integer and suddenly the second line is search and string, then it will reject.
It's an error?
It's an error.
It's an error. Okay, so that should answer your question. Who asked the question? I can't remember. You asked, yeah. So that's an error. You really have to be careful that the types here must match. So the first must always be a string, the second always a string, and so on. And otherwise, it's an error. Thank you very much. Okay. So I'm showing that a bit for longer, just so that you really store that in your brain. Values, select. It's the same level. You can change one for the other. Whenever you have a query with a select, you can also do the same with values and vice versa. It means, in particular, that the insert into values, you can also do insert into select, blah, 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 from where. That's, and I think one of you asked the question, that's how you can store a table out of a query. Insert into select, blah, 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 is how you persist the result of a query to a table. Okay, now we can also do this. Select one as A, creates a table that has one column and one record, like this. This is what a select on just a value like this would do. There's no from in there. It doesn't take any from anywhere. It just creates a new table with one record and one column. Why do I say that? Because it works in the other direction too. You can also have a query that creates a table that happens to have one record and one column. And when you have a query that returns that, then you can nest that query where a scalar would be expected. And that's magic too. Because a query, for example, this is it, select max work of the spaceships, outputs something that has exactly one row and one column. When you have that, you can nest it inside here, a multiplication. Why? Because it's only one cell in there. So when you multiply it, it just extracts the one value that there is in there and multiplies it with this, right? So this outputs a number. I automatically unbox the number from there, multiply, and that's it. I can even put it again inside the select blah, blah, blah to get back a table and so on, right? So here I put a table in a scalar in a table. You see, there's no limit. You can also compute an argmax. Who knows what an argmax is? It's when when you don't want the max, you want the value that gives you the max. And the way you do that is that you compute the max with the select max worked from spaceship. It's just computing one row, one column. And now we have this outer query that is a selection of the spaceships where the work is equal to the max. That is an argmax, right? And that is going to output the name of the spaceship as well as the max work, right? This is very common. People do this all the time. But the magic here is really that you realize this is a table in a scalar in a table. We have an inner query here, select max work from spaceships, that returns a table with one row, one column, which gives us the right to pretend that it's an atomic value, it's a scalar. So I can put it inside the where clause in an equality with the where, it's itself inside the select from where. For whom is that clear? All right, so it's really because of this equivalence between the tables that have exactly one row and one column, they are basically equivalent to the value, interchangeable. Okay. All right. I can also do things like this. where I have here an inside query that returns a table with one column. So here I have multiple records, but only one column, and I can test for whether it is in there or not. So here I'm retaining the spaceships for which the captain is in that column. So select name from persons is a list of names. And then I say where captain is in that list of names, right? So it's true if it's in the list, false if it's not in the list. That's also a common use case to do this. I can also nest tables in tables. So in the from clause, instead of giving a name of a table, I can nest a select from where. So now I have a select from where inside a select from where. I can also give it a new name and rename the columns like this very easily, right? And since I told you that whenever you have a select, you can replace it in values with values, it means you can also have values inside a from, right? You can have select inside a from, values inside a from, it's interchangeable. So here I put the values in there and I rename the columns. I think that might have been a question you had earlier. Instead of column 1, column 2, now I'm saying I want to call them S and N, and I want the table to be called T, right? So now you know how to nest scalars into scalars, scalars into tables, tables into tables, tables into scalars, tables into scalars, into scalars, into tables, into scalars, into scalars, into tables, and so on. No limits, right? You can nest all you want. It's very, very powerful, but really the best way to deal with that is to just go ahead, open a Jupyter notebook and do it. Solve the exercises, look at the past exams. This is the best way to learn SQL, and there are really, really very, very complex queries that you can do, right? At the exam, we'll ask in English, we'll ask you to write some queries that are really simple, just a few lines, and we try to push you a little bit by also asking you to write a few queries that have nestedness with a query in a query, or a query in a query, or in a query, right? So this is the idea. Any questions? Okay, that's the last slide. I'm done. This is SQL. And now you have the exercises and to exercise. So I have 2 more minutes, so I can first check that you followed, just to be sure. Next week, we are going to go back to a theoretical part with a very fancy name. It's called database design theory. Database design theory is really a mathematical theory, a lot of math in there. We look into functional dependencies, super keys, candidate keys, prime attributes, normal forms, the first, the second, the third, the 3.5 normal form, and so on. The goal of that is actually it's best practices for the design of your schemas, right? You shouldn't do any kind of schema. There are rules to follow to have good quality databases. All right, I should actually see. Oh, that's good. Okay. So the majority is above 80%, so it means you follow. And it's okay if you're below 80% or below 50, because again, just solve the exercises, do it. It's really a practical thing. The best way to learn is to just write your own queries and get used to it. Thank you very much, everybody, for attending. Don't forget the switch to winter time in 2 days. So it will be a bit later in the day. That's actually should ease things. And enjoy the exercises, and let us know if there are any questions. We're here to help you. See you next week at 10 a.m. winter time. Thank you.